Hi again. I decided to make a couple videos in chapter 6 on 6.1 and 6.3. There's a couple important points that can make it difficult, and one of the biggest theorems is in 6.3. So I thought I would do a couple videos on chapter 6. This is section, well, we'll start with 6.1, but we're on page 81 now, so we're moving right along. And of course, there's a comic. This isn't Linus. This is his brother, Rerun. I think that's right. I don't know. That doesn't sound right, but okay, let's get down here. I want to break them up into hopefully just little short ones this time, one for every little topic here. So the difference between this and chapter 5, in chapter 4, what we learned about was a random variable, x. And a random variable x could take on a lot of different values. Number of shots you take till you make a basket, number of red M&Ms in a bag. But before, in chapter 5, what we were considering is we were letting x be a discrete random variable, so its support was countable. So I gave you some examples here of either countable or finite supports, where you can basically list out, or at least list the pattern of every value that the random variable could take on. So for example, if you roll a die, the number of times you're going to have to roll until you get a 6. Could be 1, 2, 3, 4, but it goes to infinity. At least that set is countable. I mean, I can set it up. I can see, number of phone calls you received last week. Probably in maybe the sample space is 0 to 20 or something like that. But these are all things that, I guess, when I think about discrete, I think about this is a random variable where you can count or list, or practically list the things in its support. But now on continuous, you're defined, you still have a random variable x, but its support is defined over an interval. So that's the big thing that makes, here where the separation is between discrete and continuous. And because you're defined over an interval, a lot of times what you're going to have is a smooth curve that explains, probability. Let's say this is A to B. Area under this curve will denote probabilities, and in order for that to make sense, then the total region that I draw, the area under this total curve, better be 1, or else it doesn't really make sense to talk about probability, because you could get values bigger than 1 when you integrate. So here's some examples. Time you're on the phone could be, anything bigger than 0 minutes. Temperature in your room when you get home from classes, let's say. The weight of your book bag right now. This is a random variable x. X is equal to weight, and I'd say probably the weight is anything bigger than 1 pound. So anyway, that's the difference, and you'll notice now that I'll write these as intervals because the support is over an interval of values. I'm never going to write, like the time you're on the phone, we're not trying to say convert, or not converge it, but round it to the nearest minute. So it's not like 1 minute, 2 minute, 3 minute. That's not the support I want. I want to say the time I'm on the phone is bigger than 0 minutes, where it could be, pi minutes or something like that. So what's special about a continuous variable then is kind of what I alluded to up here. You have to have the area under, you'll have a density function again. Well, in chapter 5 we called it a mass function, but now we change language and call it a density function. Basically the same thing. It's a function that describes probability. But to find probability, you have to integrate under that f of x curve. So, and if you look from a negative infinity to infinity, I mean, a lot of these could be 0. Of course, this is all 0 here and 0 here, but over that interval, that guy better integrate to 1. And also, this kind of makes sense. Your density function has to be positive. Here's a density function, f of x. Let's just say that could, here's my number line. This is the x-axis. I mean, maybe this area right here, I'm sure I could find values that make it integrate to 1, but this wouldn't make sense at all because you could have a negative probability. So I have two things with f of x. He better be always above the x-axis. That's what condition 1 is saying. And condition 2 is just saying the area under the curve of f of x over the long haul, over everywhere f of x defined, has to be 1. So a couple properties then to find probabilities, like the probability the random variable takes on a value between a and b, you're just going to integrate f of x over a to b. And the difference between this and in chapter 5 is we were summing f of x over its support. Well, actually, in chapter 5 we called this p of x. I mean, it's just another name for a function. We could call everything f of x and it would be fine. Anyway, the difference is we integrate. With continuous, and this is not true with discrete, we have no probability exactly at a point, because by definition the probability of a would be going between integrating the function f of x between a, and that is 0. So it's impossible on a continuous random variable to ever say I'm going to hit exactly one point. And because that's true, all of these are equivalent. Because when you integrate, you know, it doesn't matter. Oh, I'm trying to draw a picture here. Let's do this again. It doesn't matter if I integrate between a and b where I don't include them, because it's still just the area between the two. So these are definitely equivalent. It doesn't matter if I include the endpoints or I don't include the endpoints. I get the same value because I'm integrating. And the endpoints have an area 0 anyway. So so I just did a few examples, and you can see what I'm trying to do is that maybe I'm taking just something that, you know, you had around to get values for, again, battery lifetimes, and I put them into bins. But what a continuous random variable is trying to fit a distribution, here's the red line, to that situation. And then to find probabilities, I'm just going to integrate over different regions. So I think that's probably, I mean, the big point. I showed you an example here. You know, what's the probability, you know, what is this guy a legal density function? I can show you, you know, he's always above the x-axis. Oh, I don't know why that keeps doing that. Yeah, this guy's always, as you can see, above the x-axis. That curve is down here. Let's see, I'm just showing you that he integrates to 1 over his region. I mean, notice again that I'm giving you an interval for the support. What's the probability a battery lasts more than 4 minutes? I'm integrating from 4 to infinity. So the big thing is now you're going to see an f of x, you're going to see integration, and properties just being a little bit, I don't want to even say different, it's just because we're integrating now. Here's a density function I gave you. F of x is 1/9 from 0 to 9. If you integrate from 0 to 9, 1/9, the area under here, oops, that's 8, here's 9. The area under here is 1. You can just look, it's a rectangle. The probability that x is between 5 and 7, I just integrate between 5 and 7, or if you have a nice picture, you can just geometrically say what that probability is. You're allowed to do it that way. That's absolutely fine. Here's another random variable. It's a very, very nice one, a nice polynomial defined over an interval. This came up on the quiz. I just want to make sure when you see this language again, don't forget that we had done this a given b back in chapter 3. So I think a few people on the quiz were not sure what I meant by that. That's a nice example. Yeah, so I'm going to stop here. This is really going to be then continuous random variables that we're looking at the probability density function, little f of x, and its properties. And I'll make one for the CDF next.